All right, so here's where we were at. We have our tables and our fancier chairs. Yeah. And we have 1,200 small components, 800 large components. We want to know what we can do to make the most profit, and then we have this other thing that would tell us the profit. Okay? So we're trying to break this down in a mathematical or algebraic way that we can look at it so that we know for sure what the answer is instead of guessing and checking lots of different things. Okay? So equations and inequalities are going to help us do that. The idea is let's try and discover the right set of them and try and understand why those work. So first thing we want to do is think about what we are solving for. We are solving for a number of tables and a number of chairs, right? Okay. So those are the things I want to be my variable because when I finish the problem, I want them to tell me this amount of tables or this amount of chairs. So I'm going to go ahead and set up a system of variables that revolves around tables and chairs. So I'm going to call, and you can just add this information to your math moment, or you can watch because we're going to do the same thing on the worksheet, and you can just do it there later, okay, as long as you're engaged and thinking about it. So we want to find tables and chairs. So how about we make x equal to our number of tables and y equal to our number of chairs. Is that okay with everybody? All right, now that already takes up my x and y variables if I'm going to use them in that respect. Okay. Now, to calculate profit, it depends on both how many tables and how many chairs you have, right? When you guys were calculating profit, if we look back at the problem, since you guys knew you made $12 on a chair and $18 on a table, when you guys were coming up with different combinations of numbers of tables and numbers of chairs, you guys were taking, okay, this many chairs times 12, this many tables times 18, and add it together for your total amount of profit, right? So when you're calculating your profit, you are dependent on both the number of tables and the number of chairs that came up in your solution. This means our profit equation, you're going to see noted now, kind of a weird notation. P is just a random name for it, probably, because we're talking about profit. I chose P, right? Normally, you see something like f of x or p of x. This time, we're going to say p of x and y. Does anybody know why I am choosing to allow p to have x and y here next to it? Yeah, I have two variables I have to plug in to calculate my profit, and they're not the same. When you guys were plugging in x3 for x and f of x, that was because the f function only depended on x, right? There was only one number that you could change and plug in. For our profit equation, there are two, okay? And so x was our number of tables. How much money did we make per table? 12? 18? So 18 times x is how we calculated the profit from the tables. And then we made $12 for each chair, right? So 12 times y is how we calculated the profit from the chairs. And then we added those together for our total profit. Okay? So this equation is sometimes called your objective function because your objective is to make the most amount of profit, and this equation is going to tell you if you've reached that objective or not. Okay? Now, this is not something I can graph on an xy axis because this is like not y, right? It's something I plugged both x and y into. So this is not something we can graph, okay? But it's what we plug our answer into to see where we're at. So then I got to go back and see what else is going on there. The other thing that was going on were the restrictions, okay? Oops, wrong one, sorry. So the restrictions here were 1,200 small components and 800 large components. Now, my variables are not small components and large components, right? My variables are about tables and chairs. That's okay. What I'm going to try to use is my variables about tables and chairs. I'm going to try and translate them into something that counts the number of a certain type of component to write a restriction for it, okay? So let's say I wanted to concentrate on this first. Here's a restriction. 1,200 small components is all that I am going to get. Okay? That means my total amount of small components needs to stay less than or equal to 1,200. Right? Is that fair with everybody? So there is something that needs to stay below or equal to 1,200. And that is the number of small components I use. That's nice, but now I need to figure out how do I write the number of small components that I'm using in terms of my variables, x and y, that don't represent the number of components. Like I can't just say, oh, x has to be less than or equal to 1,200. No, because my x represents the number of tables, not the number of components. Does anybody know an expression I can put on this side that would represent the total number of small components I use in terms of x and y, so that I can attach that to the fact it has to be less than or equal to 1,200. So when you guys were doing the Lego problem and you were seeing, okay, like group 1, for example, says 400 tables, 100 chairs. And then they said, ooh, just kidding, can't do that. Why are they saying they can't do that? Jake? Yeah, that would require more pieces than there are available. So there is a way to attach number of tables and chairs into number of pieces I'm using, because they wrote that up there and knew that they exceeded the number of pieces. So I'm asking you right now, what could I write here about small components, but the equation is going to use x meaning number of tables and y meaning number of chairs? Ashley?
3x plus y.
Okay, so 3x plus y. I think we might have mixed up our variables, but your idea is right. Or x plus 3y, right? Okay, so x plus 3y. Where is she getting this from? Yeah, Michael.
The number of small components in each
Good. So my total number of small components is going to be one small component for every table, right? Plus 3 small components for every chair. And when I calculate that all up, it better be less than or equal to 1,200, because that's all the pieces that I was given. Is that okay with everybody? So my restrictions are based on whatever the physical restriction was they gave in the problem. They said less than or equal to 1,200. I'm going to write you an equation about being less than or equal to 1,200. But I'm going to write it on the variables about the things I want to find. Okay? All right, so what was our other restriction? 800 big pieces. Okay. And what would be the expression on the left side of this inequality that would have to stay less than or equal to 800? Michelle? Say it again. Good. So 2x plus y, because in every table I use 2 large components, and in every chair I use 1 large component. So if I add all this up, I'll have my total number of large components, and it needs to stay less than or equal to 800. Okay? So this tells me why, group 1, I'm not putting you guys on the spot. It's actually a good learning experience for people, right? So this tells me why their 400, 100 isn't going to work, right? If I plug in their 400 tables, 2 times 400 is 800, plus 100 is 900. Is that less than or equal to 800? No, they exceeded the number of large components, right? They don't fit that inequality. So these inequalities are creating boundaries for us that are going to show us, ooh, you have to choose stuff that's in between here. Okay? Is this all right with everybody? All right, so I'm actually going to make my own graph, I think, rather than use this one. Well, maybe. Maybe it's unmovable. Just kidding. Okay, I'll use this one, but we're going to change it a little bit. Okay. I'm not going to use their x and y axis, and here's why. There is also a physical restriction on what's going on in our problem about x individually and about y individually. Okay? What are your possible number of tables that you could make? So the number of tables must be what? Okay, so we know less than or equal to 400 because of our other stuff up there, so you're right. I don't want to take that away from you. Okay? But without doing any math from the other equations, just in a realistic, like if you are making tables and you're doing a physical thing, what is true about the number of tables? Yeah, and you're totally right. I don't want to take that away from you. You were thinking deeper than I even needed you to go right now, all right? So the number of tables has to be greater than or equal to 0. Maybe you'll choose 0, but you're not going to say, I'm going to make -5 tables today. Okay? Doesn't work. All right, and then what could you say then about the number of chairs you're going to make? Same thing, right? So I don't really want this whole XY coordinate plane thing because I already know I have to be making more than 0 tables and more than 0 chairs. So I would rather have just like the first quadrant. Do you guys get what I'm saying? Because I know that I got to be there. Okay. So this boundary line right here, that x is greater than or equal to 0, remember that's a vertical line on the y-axis. And our y is greater than or equal to 0 is a horizontal line, so on the x-axis. So I'm making this, sorry, messy. Do not like it. Okay. So we're going to call this my x-axis, and this my y-axis. I'll fix that. All right, so first, restrictions that are easy to graph. So this is a vertical line at 0. And I want to shade the area. Remember how you graph inequalities on a graph? It's like not just a boundary. It's like everything on this side of the boundary. Okay? So x is greater than or equal to 0. If this is my y-axis, that's a line that follows along the y-axis. And then everything over here would be shaded. Okay? I don't want to shade it right now. Is that okay with you guys? We understand this whole graph would be shaded. All right, you'll see why. I got a lot of shading to do. Okay? So I don't want to mess it up right now. So then this boundary right here, y is greater than or equal to 0, is this horizontal line. And then we would only shade above it. Okay? So this whole quadrant would be shaded right now. Again, it's the same reason why I chose to just use a first quadrant graph rather than all 4 quadrants. Is that okay with everybody? All right, so this is my 0, 0 point down here. All right. Now I got to graph these inequalities, okay? So if things, you can change them to slope-intercept form if you want, okay? But there is a quick way to graph lines when they're in standard form. Does anybody know what that is? If I have this equation, x plus 3y equals 1,200, let's say it just was a line and not an inequality. What could you figure out quickly about this line in standard form without rearranging everything? Good. So it's easy when it's in this form to plug in 0 for x or 0 for y. When you're doing that, what are you finding? The x and y intercepts, okay? So I'm going to go ahead. Let's see. I'll do this one in red. So I'll graph this inequality in red. Okay, so if I plug in 0 for x, I hate the cover-up. I hate that people just call it the cover-up method, okay? But if you understand, it's because you're plugging in 0 for this, and 0 then has no value, so the equation becomes 3y equals 1,200, okay? So if we're looking at 3y equals 1,200 and we divide by 3, we're going to get y is equal to 400. So 400 is our y-intercept, okay? What are we going to get when we plug in 0 for y and find our x-intercept? 1,200, right? If we plug in 0 for y, 3 times 0 will be 0, the y will be gone, and we'll just have that x is equal to 1,200, okay? So for this line that I'm going to graph in red, I need to graph an x-intercept at 1,200, 0, and a y-intercept at 0, 400. To think about the scale of my graph, right? So I'm going to do the next one, too, so I don't mess it up. All right? So the next one, yeah, Lauren? We'll deal with the shading part in a minute, yeah. Okay? So we do have to do with that, but right now I'm finding how to get the boundary line, so I'm treating it like a line. Like, here's how I get the boundary. Because it is an inequality, we do have to do the shading on the graph. I'm going to make that decision separately. All right, so this second equation, I'll go ahead and do in purple. Okay. So for this equation, when you go to find the x-intercept, so you plug in 0 for y, you get 2x equals 800. So you get x is equal to 400. So the x-intercept for that boundary line will be at 400, 0. Okay. And then the y-intercept, if I plug 0 in for x, I'm going to get y is equal to 800. So the y-intercept here is 0, 800. So I'll just go ahead and label my graph by hundreds, I guess. So 100, 200, this kind of thing, okay? So each of these will be 100 here as well. All right, so when I put this first line on there, again, I'm just doing the boundary, okay? The boundary is a line that crosses through these 2 points, okay? So 1,200 on the x-axis, 400 on the y-axis. There's 400 on the x-axis, or on the y-axis. 1,200 on the x-axis. Now, when I draw the boundary line in, should it be solid or should it be dashed? Solid, okay, because of the equal to part of the inequality. Okay, we could choose points along this boundary. So I draw it in. Sorry that my line is not very straight. I told you I need lots of points to draw straight lines up here. Okay. Now Lauren's right. There is a shading aspect going on here. Okay. The question is, which side do you shade? Well, think about if you solved this equation for y, would you say that y is greater than or less than the boundary once you've finished solving the equation? It would still be less than because you'd move the x to the other side, right? And then you would divide by +3. So is anything going to cause this sign to change direction with the y value? No. So it's going to be y is less than or equal to whatever it comes up to. Okay. That means the y points along this boundary, you want to include them, as well as all the y values below them. Think about if you picked a point on this line, which direction would you travel to capture y values below the one that you're at right here? Downward. That's the direction that we'd want to shade, okay? So it shades all over the graph, but remember, we already have these other two boundaries kind of closing us in the first quadrant, so we're really focusing on this area here. So if our only restriction was that we could use 1,200 small components, these points in here, like this point's a possibility, I could make 400 tables, okay, and 100 chairs. Okay? If that was our only restriction. Right? That's a possibility. But we have this other restriction that we now have to graph as well. Okay? More than one restriction. So I'm going to go and put this on the graph. This line crosses the x-axis at 400 and the y-axis at 800. So I'm going to go ahead and plot those points and draw the boundary line. Again, solid or dashed for this boundary? Solid, okay, because it's included. So, yeah, okay. There's my boundary line. Okay. And again, if you solved this inequality for y, would y be less than or greater than once you moved everything else to the other side? Okay. So you would move the 2x to the other side. And then you don't even have to divide by anything. So is this sign going to change direction? No. So y is still going to be less than or equal to whatever you have on that side. So again, think about if you were on a point on this line and you wanted to capture the y values that were less than that one, you would move down. That shades this side of that line, right? Okay. So here's all of my restrictions graphed. And here's what that has told me. If I have to be within the boundaries for both of the restrictions, I need to be in this area right here. Does that make sense to everybody? Those are the points that would work. Tables, comma, chairs. Okay? So now you see why 400, 100 didn't quite work, right? They were outside of one of the restrictions, and that's why that wasn't a possibility. But if we look at like group 2 says 300, 200. Okay? So 1, 2, 3, 1, 2. Whew, it's going to depend on my line if that's in the boundary or not. Okay? Close. Okay? But I drew my line freehand, so it's a little bit hard for me to tell. All right? Another group says, let's see, group 8. You guys said 200, 333. 200, 1, 2, 333 seems like it's in there. Okay? So you can see where the possibilities are. But here's the thing. If we want to maximize our possibilities, those things are going to happen at the ends of this quadrilateral that we have created. Okay? So these endpoints here are the options that we really want to focus on. Some of them are easy to see what they are, and some of them are more difficult. So one option is 0, 0. Well, these both maximize and minimize. If you make no chairs and no table, how much profit are you going to make? $0. Probably your minimum, okay? All right, so here's another option. This is at 0, 400. So this means what if you make no tables and 400 chairs? This option down here is at, is that 4 also? Yeah. Is at 400. What if you make 400 tables and no chairs? And then there's this fourth option out here. Now, I graphed it by hand. I didn't have a ruler. That option is a little hard for me to just tell what it is. How could I get the exact values at that point? Yeah, Jason. Use elimination and substitution to solve the system of equations. What are the two equations that are crossing right there? So the two lines that we're crossing right there are these two things right here, if they were just equations and not inequalities, right? Because I'm just talking about the line part of them right now. So basically, I want to know, where does x plus 3y equals 1,200 meet this other line, 2x plus y equals 800? So I'm going to solve this using substitution or elimination. Okay? Again, why? My graph gives me a nice pretty picture of what's allowed and what's not allowed. But because I graphed by hand, it's difficult to find exact things when they're in between other things. Okay? All right, so I don't know. What do you guys want to do? Get rid of x? All right, so like multiply this by -2. Is that what you're saying? Yeah? Okay, so let's multiply this by -2. So that will give me -2x minus 6y equals -2,400. And then here I will still have 2x plus y equals 800. The x's will cancel. I will have -5y equals -1,600. And then I will divide both by -5. And so I will get that y is equal to, let's see, 20? Okay. So what did I just find out? Okay. Graphically, I found out that at this point where they cross, the y coordinate is 320. But what did I find out in the context of my problem? Yeah, that there's an option for me to make 320 chairs as a possible way to maximize my profit. Okay? And the number of tables that would go with that I can obtain by plugging 320 back into one of these equations. So let's say I plug it in here. 2x plus 320 equals 800. So I'll get 2x equals 480. So x is equal to 240. All right, so I have 4 options. Okay, my options are 0, 0, which means don't make any tables or any chairs. Another option is 0, 400, which means don't make any tables and make 400 chairs. Another option is 400, 0, which means make 400 tables and no chairs. And then my fourth option is 240, 320, which means make 240 tables and 320 chairs. So what I'm going to do is I'm going to check by going to my profit equation and plugging them in. Okay, so let's split up the work. We all know 0, 0 is going to make us nothing. Okay? All right, these three groups over here, groups 1 through 3. Can you guys please plug in the 0, 400? So if we only made 400 chairs, how much money are we going to make? Okay? Group in the middle. You guys plug in 400, 0, so 4, 5, and 6. Okay? If you only make 400 tables, how much money are you going to make? Groups 7, 8, and 9. Plug in 240 tables and 320 chairs. Sorry, you guys have hard work. And then tell me how much money that we are going to make. What we do is we plug each of the possibilities back into our objective function, our function that calculates our profit. And from that, you guys can see, okay, you either make $0, 4,800, 7,200, or 8,160. The 8,160 is the maximum that you could make, so you would choose to produce 240 tables and 320 chairs. Did we get anyone in this class that did it? Yes, group 6. Good job, you guys. Yay. All right. Do the other classes have some people? 2 in 4th period? Oh, 3. 3 in 4th period? No, I covered yours up. Oh, no, I didn't let them put it up till they all put it up at the same time, just like you guys. All right, so do we get the process? Okay. So we have to identify what we're solving for. Once we find those, there's going to be some restrictions in the problem. The restrictions make the inequalities that help us find the feasible region, they call this. Okay, those are all the possibilities, the feasible region. The vertices of your feasible region are your possible places to maximize or minimize the situation. I know we're in the mode of thinking maximum profit, but sometimes people want to minimize waste or something like that, okay? So these would maximize or minimize what's going on, and then we plug them back into our objective function. Okay? So here is an overview of the process. You don't have to write down my overview if you don't want, okay? But you should write down some overview so that if you're at home working on this worksheet tonight, okay? So first of all, what we did, define your variables and write constraints using your given information. Don't forget the common sense constraints, like the fact we were locked in the first quadrant because we had to have more than or equal to 0 tables and more than or equal to 0 chairs, okay? So your variables, you always want to be like the thing that you're solving for, okay? So that you're able to get through the problem and answer them. Like even though the problem was about components and about money, my variables were number of tables and number of chairs because that was going to help me find my solution. Those are the things I wanted to solve for. Once you write your constraints, you graph your feasible region and you find the coordinates of each vertex. Sometimes it's easy. Sometimes you have to use a system of equations, substitution, elimination, like we did to find one. Okay? Then you write the equation for your optimization function. Okay? That's the equation that calculates your profit. So you can tell if you've maximized or minimized whatever you need to. And then you evaluate that for all your options and decide what you want to do. Okay? Again, you don't have to copy this word programming handout. If you didn't copy it, I'll put it back up at the end. And also remember, it's on the video. You can pause it and watch it for as long as you want. Okay, so in order to raise money for homecoming, your class needed a way to raise money. Okay. ASB decided that a sale fundraiser would be the best option. The student body decided to order cases of Hershey's chocolate bars and cases of jarred popcorn. However, the student body also decided the class could order no more than 400 candy bars and jars of popcorn and spend no more than $500. How can the class maximize the profit? So first of all, our restrictions are right there, right? No more than 400 total objects, bars and jars of popcorn. And you can't spend more than $500. Hershey's chocolate bar comes with 30 candy bars in a case. You pay $10 per case. You sell it $1 a bar. What's our profit on each case of Hershey's bars? 20. Okay, popcorn comes with 10 jars in a case. You pay $20 for the case, but you sell it for $5 a jar. So what's our profit there? 30. Okay? Are we okay with the scenario? All right. So, okay, so notice first that they defined the variables for you, but notice those are the things that you would have to have figured out in the problem anyways, right? You want to maximize profit and figure out what your order is going to be, but you have to order by cases of Hershey bars and cases of popcorn, right? So they said, let X represent the number of cases of Hershey's chocolate bars, and let Y represent the number of cases of popcorn. The cases versus the individual amount here is a little bit, got to think about it a little bit. Okay, it's not so automatic. So we'll think about what's going on. This chart is supposed to help you. You can use this chart on your own project when you see what that looks like as well. So you guys are going to create your own business idea, if anybody looked at the project, okay, where you're going to sell two things. We've had lots of different ideas, okay. Some people sold sunshine and rainbows. One of my favorites, tacos y gatos. You go buy a taco, and you can buy a robot cat to take home with you, okay? So they sold tacos and robot cats, okay? And in the project, you're given a restriction of $10,000. So $10,000 is the restriction of your spending. So what you would tell me is, well, this costs this much for me to produce, and this costs this much. So that, if it costs me $3, say it costs me $1 to produce every taco and $5 to produce every cat, then, and X is my tacos and Y are my cats, then X plus 5Y needs to stay less than or equal to $10,000. The other restraint you're going to create yourself. So it could be something like, I only have this much space, something like that. So you're going to create one restraint, one's kind of built in for you. And you're going to make it so that it works out like the Lego problem. You're going to graph a feasible region, you're going to have some possibilities, and figure out which possibility maximizes your profit. So start thinking about the business that you'd want to make. All right. So the number of cases of Hershey bars goes in here. We don't know the answer to the problem, but a variable has been assigned to this, right? The number of cases of Hershey's bar is X. Okay. And the number of cases of popcorn was assigned to be Y. Okay. So if in this problem you ever want to use the total number of cases ordered, that will be represented by X plus Y. Okay, so this is just kind of organizing the thought process, this table, but you have to know how it works to help it organize your thoughts, right? Okay, the number of units is different than the number of cases, because when you order a case of Hershey's bar, how many units do you get? 30. So the number of units, if we're only working with X and Y variables, the total number of bars that you order will be represented by what? 30X, okay? 30 times however many cases you order. You order one case, you get 30. You order two cases, you end up with 60 units, okay? What is going to be my number of units for popcorn jars? 10 1. And so if I ever want to add up the total number of units, that would be 30X plus 10Y. Now, I see rationale for wanting to add up the total number of units. What did they tell us in the problem that is related to this 30X plus 10Y expression? Good. I cannot exceed ordering 400 candy bars or jars combined, right? So this is going to end up having to stay less than or equal to 400, okay? So I'm going to actually just go ahead and jot that right next to this. I don't really know much about this, but this one I know something about, okay? All right, the cost, okay? What I have to put out to buy things, okay? What is the cost going to be for my Hershey bars? 10X, because it costs me $10 per case, right? And X represents the number of cases. So 10X, because if I buy one case, 10 times 1 will cost me $10. If I buy 5 cases, 10 times 5 will cost me $50. Okay? What about my cost for my popcorn? 20Y. So the total amount that I'm kind of shelling out at the beginning to buy these cases of Hershey bars and popcorn jars, Dr. Seuss. Okay. 10x plus 20y gives me my total, which needs to remain less than or equal to 500, because if you look back at the problem, they said ASB is only going to let you spend $500 in order to run your fundraiser. Okay. Now our profit. Okay. How much profit do we make on each case of Hershey bars? Okay, so we sell $1 per bar, which means we get $30 back, but that's not completely profit, because how much did we spend on the case? $10. So how much are we making profit? $20. So $20 for every case of Hershey bars will be profit. Okay. And what about for our jars of popcorn? 30y. Okay. So 30 times however many of those I ordered. So my maximum profit, or my total profit, will be 20x plus 30y. This is the equation that I'm plugging in points, those vertices from my feasible region, to see what the maximum is. So this is like my profit equation, okay? The function I'm trying to optimize. Any questions about how we figured those things out? Okay, so what you're going to be doing today then is walking through the rest of this process so that we can answer questions about this on Monday, so that as you're assigned your project and you're working on it, not only did you see us do the process with the Legos to kind of capture the general idea of why you'd want to do it and write down a note of the process, but you've actually tried it once on your own so that you're able to get through your own business model and do that as well. So, what you're going to be expected to do after this, notice, write the restrictions and simplify them. You don't need to change their form. We actually already wrote our restrictions, right? What are our two restrictions? Where are they coming from? The number of units and the cost. You have two inequalities. You could graph those inequalities by finding the boundary line. You can rearrange in slope-intercept form if you want to. Be my guest. I think it's much easier to find the x and y intercept. Then it says to write the objective function. We already wrote the objective function. Where are you going to get that from our table? The profit. The equation that we wrote for the profit is our objective function, because our objective is to maximize profit. I'll be honest. Some of these things we borrow from other people and whatever. I don't think there's any simplifying to do with your equations, because you want the actual x and y intercepts. So with our inequalities, I think they were thinking write them in slope-intercept form, but I don't think you guys need to do that. I think it's easier to graph them the other way. If you want to, you can. I don't want to, so I'm not going to, but you can. Here, so you can just graph it on a separate sheet. You don't have to actually cut it out and glue it onto this. You could just like staple it or whatever. But you're going to create the graph and label your vertices. So you're going to get your two restrictions on there. Now, there's also a couple of restrictions we didn't put in, but what are the real-life restrictions, kind of independent of what ASB tells us we can spend and stuff like that? Samantha? Yeah, that x has to be greater than or equal to 0 and y has to be greater than or equal to 0. We're not going to order -3 cases of Hershey bars, okay? People would get the order and be like, what the heck, okay? Be kind of nice if you could do that. I guess they would owe you money that way. I don't know, maybe. All right, so you're going to put the graph there. Your graph should have all the boundaries. It should have the shaded feasible region, and you should find the endpoints. Once you find the vertices, you should put them here, and then you're going to evaluate P at each vertex. So you're going to plug them each into your profit or your function that you're trying to optimize, and you're going to find that, and you're going to answer the question, when is the maximum profit and where will it occur? Or what is the maximum profit and when will it occur? So you're going to tell me, this is the maximum amount of money we can make through this fundraiser. It's going to occur by ordering this many cases of Hershey bars and this many cases of popcorn jars. Okay? Does that make sense? Yes?
They're saying that they're going to sell everything you order.
Well, Right. So that's a risk that you take. But if I'm trying to plan the fundraiser and I have these restraints to work on, I'm going to order the things that are going to sell me the most, and then I'm going to pressure. You guys know that are involved in any activity, right? You need to get someone to buy at least 5 of these, right? You know the pressure. That's because that person has figured out the amount of money you want to make. They have pre-ordered those objects, and you're only going to make the profit if you sell them all. So that's where, like, the real life pressure comes in, right? I got to sponsor my sister in a basketball shooting contest. Okay, $1 for each free throw